Each day, most of us walk, turn, and run without any hesitation. The muscles in our bodies work in unison as we effortlessly glide through our environment. Exactly how those movements occur is largely dictated by sensory data like vision and proprioception. This data informs the brain of the state of the world and our body, which helps to plan what a movement should look like. The problem is that even in healthy people, that sensory information is very uncertain. For example, light conditions, age, and ambiguity, among a lot of other things, lead to uncertainty in what we see. With proprioception, there's also a lot of uncertainty, as you can see from this figure here. Now, with mobility, an accurate understanding for where our feet are in relation to our center of mass is vital to avoid getting hurt. So how does the nervous system control such complex movements when the data available is so uncertain? Luckily, an English statistician named Thomas Bayes developed a model that helps us draw conclusions with variable data. Simply put, Bayesian inference suggests that the best guess for a parameter, when the available evidence is uncertain, comes when we combine that evidence with prior knowledge. In the context of movement, this means that the ideal estimate for a body position comes when the brain considers the current sensory data as well as learned expectations of body position, based off many previous attempts doing similar movements. And the variability of each source of information dictates its influence on the final estimate. For example, consider the estimate of foot position while climbing stairs. As the leg is lifted to clear a stair, sensory data from the legs relays information that is clouded with uncertainty. But the nervous system has learned that the outgoing motor signals usually lead to clearing the foot of each stair. Combining both of these data sets, the nervous system makes an ideal estimate for the foot's position. Now, Bayesian inference in motor control has been reliably shown in the last decade. However, the majority of this work has used only simple upper extremity movements. So the purpose of this study was to see if the Bayesian-like behavior seen in hand movements is consistent when calculating the position of center of mass during full body mobility movements. We anticipated that as uncertainty of sensory feedback increased, people would rely more on their expected location to compensate for the uncertainty in the data. To do this, 30 healthy females completed a VR protocol where they moved their center of mass to various targets with a single step while receiving limited visual feedback. In this protocol, participants control a pink cursor in VR with reflective markers placed at their center of mass. Motion capture cameras record the marker's location and stream it into the VR headset. The goal is to get the cursor into the target box, but they only get to see it midway through the movement. This forces them to estimate their body position as they step toward the target. When they feel they're in the right spot, they push a button that shows the actual cursor location. Now, starting off, everybody's expectations are different. So we needed to get everybody on the same page as far as expected body positions go. To do this, they first complete a training block that implicitly teaches them to expect a backwards shift of the cursor. On each trial, the moment the cursor leaves the start box, the unseen cursor is shifted backwards, ultimately forcing them to move further than needed to hit the target. The amount of shift on each trial is randomly chosen from a normal distribution centered on 7.5 centimeters. Ideally, at the end of the training block, the distribution of their final center of mass positions should mirror the distribution of the shift, showing that they've learned to expect it in their movements. This video showing the training block of one participant indicates that she unknowingly did learn to expect the shift in her movements. After the training block, they complete 5 more blocks with the same cursor shift, but with uncertain visual feedback of the cursor location partway through the movement. We did this by adding noise to the cursor location or removing feedback altogether. This forced them to make an estimate with uncertain sensory info to rely on. The size of noise varied between 2 conditions, resulting in 4 different conditions of visual uncertainty. For the analysis of each participant, we plot the shift on each testing trial against the accuracy and use the linear fit between the two as our outcome metric. In this figure, a slope of the regression line with a slope of 0 would indicate a complete reliance on what they see. Or in other words, the expected shift had no effect on their estimates. A slope of 1 would indicate a complete reliance on the expected shift, meaning that Regardless of what their vision told them, they compensated by moving 7.5 centimeters too far. Now, we anticipated that reliance on expectations would increase with visual uncertainty, which would be shown by an increase in slope across the 4 uncertainty conditions. And as you can see from these figures from a single participant, this participant's data is in line with our hypothesis, showing an increase in slope across the uncertainty conditions. And when you combine it with the group data, as seen here, showing the slopes of all of our participants across the conditions, we saw a significant increase in reliance on the expected body position as sensory data became less certain, confirming our hypothesis. Now, what does this mean for our original question? This confirms that it's not only sensory data from our muscles, eyes, and skin that inform us how stable we are. But similar to hand movements, it's also stored expectations of the outcomes of our movements, meaning that therapeutic practices aimed at decreasing the effects of age, disease, or injury on sensory processing may do well to include the development and updating of accurate movement expectations. Also, training regimens seeking to improve athletic performance may benefit from including measures to decrease sensory uncertainty, or construct expectations of body position that are better, more accurate, and better fit complex motor skills. Looking forward, we plan to explore the role of proprioceptive uncertainty in the Bayesian framework and how it contributes to overall sensory motor function. And with that, I'd like to thank all of my many supporters, both financially and emotionally. And I imagine that I'll have some questions. Thank you very much.